This is a video lesson on interactions. To begin with, we had two types of interactions. The first ones are electron target interactions, and those occur in the X-ray tube. Specifically, we have electrons that go from the cathode to the anode, and we produce infrared, BREMS, and characteristic radiation. On the other hand, we have interactions where X-rays come from the X-ray tube and they interact in the patient. So these are called interactions with matter. And we're going to only look at three of these for the registry content purposes, and that's coherent, Compton, and photoelectric. There are two others, pair production and photodisintegration. So let's begin with electron target interactions. What exactly does that mean? It means the electrons which are coming from the cathode are going to strike the anode, which is called the target. So it's the electrons that are coming from the cathode that are striking the target, and that's the component or part of the anode, and we're going to produce our X-ray beam. Before we talk about the interactions that occur in the X-ray tube, let's talk about X-ray production. We first of all need a source of free electrons, which is where we get them. The origin of this is thermionic emission. Thermionic emission is boiling off of electrons, and that occurs at the cathode. Acceleration of electrons is where we have kVp. We're going to push the electrons with the kVp. Focusing of electrons is going to happen due to the focusing cup, which concentrates the electrons toward the target. And finally, deceleration of electrons is at the anode, and at that deceleration is going to result in our BREMS and characteristic and infrared interactions. So let's begin with the first interaction. So infrared. Infrared is an interaction that's going to result in heat. So this is something we have greater than 99% heat is produced when we produce X-rays, and so we have a very inefficient process. The projectile electrons interact with the outer shell electrons of the target atoms but do not ionize them, meaning they do not knock out an electron. The outer shell electrons are raised to an excited or higher energy level. The electrons drop back down to their normal energy state with the emission of infrared radiation. So it's just a matter of having heat coming from the anode. In the BREMS interaction, the projectile electron, which is coming from the cathode, is attracted to the nucleus of one of the atoms that's on the anode. So it slows down. The electron changes direction, losing energy, and the lost energy is emitted as an X-ray photon. The amount of energy of the X-ray photon specifically is equal to the energy where it started with the electron started with where the energy ends with that electron. So E1 minus E2. This interaction can occur at different distances from the nucleus, results in different energy, and gives us our heterogeneous beam. In the BREMS interaction, we have a projectile electron, which is a negatively charged particle that's coming from the cathode. It's going to be attracted to the nucleus, which is positively charged on this atom. It's going to change direction because it's going to get kind of sidetracked, and then the loss of energy is our X-ray photon that results in this process. We can have this occur at different distances from the nucleus, so therefore we can have low energy, medium energy, and even high energy BREMS X-rays. In the characteristic interaction, we're going to have a projectile electron that interacts with an inner shell electron this time. Since it's going to remove it from its orbit, we have ionization, and that's important. The outer shell electron fills the void in the inner shell, and when the electron transitions, energy is lost. It's called a characteristic X-ray. the X-ray has energy equal to the difference in the binding energies of the orbital electrons involved. Now, the thing is with useful characteristic X-rays, we have all different characteristic X-rays that are produced. We have K-shell, M-shell, M-shell, etc. But only K-shell X-rays are going to make it through the filtration, meaning that they have enough energy to do so. So the K-shell X-rays with an effective energy of 69 keV are useful for making a diagnostic X-ray. And that is there provides a homogeneous beam because we have 69 keV. Now, this is part of our useful beam though. So K-shell characteristic X-rays require two potential of at least 70 kVp because of the K-shell binding energy of tungsten. So this is an example of showing you the effective energies of the K-shell binding energy, K-shell X-rays, the L-shell X-rays, the M, the N, and the O. The only X-rays that will make it through our filtration are the K-shell X-rays. The others will not make it through. They will be absorbed by the filtration and therefore do not contribute to our image. Under 70 kVp, 100% of the X-ray photons produced are BREMS X-rays. Over 70 kVp, 85% of the X-ray photons produced are BREMS. Now we're going to talk about X-ray interactions with matter. So with X-ray interactions with matter, we have X-rays coming from the X-ray tube, which is our primary beam or useful beam, and they're going to interact with our patient, which is the matter. We can have absorbed X-rays, which are totally absorbed. That would be the photoelectric interaction. And we can have X-rays that are partially absorbed and then result in scatter, and that's going to be the Compton interaction. We also have remnant radiation because the scatter radiation and non-interacting photons can make this part up. And remnant radiation is also called exit radiation. And that makes up our image on our image receptor. The coherent effect is our first interaction we'll take a look at. We're going to talk about this interaction as having other names which are unmodified because it has the same energies with which it starts. We're going to talk about it also being called Thomson and classical. With this interaction, the incident photon, which is the incoming photon, the incoming X-ray, is going to interact with an atom. So it's going to interact with the entire atom, causing it to become excited. Scatter is emitted with the same energies it started with, and that's why it's called unmodified. It's not changed. So we have a change in the direction of the X-ray without a change in the energy. That's a key for this interaction. But it does result in scatter. The Compton interaction is an interaction where we have an incident photon, an X-ray photon, interacts with an outer shell electron or otherwise loosely bound electron and is partially absorbed by the electron. The electron is emitted from the atom, which is called ionization, and it's called a recoil electron or a Compton electron. And the remaining or leftover energy is emitted as scatter. Now in this interaction, we have a change in energy. So this interaction is called incoherent or modified scatter. Incoherent or modified scatter. With this interaction on the left-hand side, we can see an image where we do not have scatter or the gray appearance, but on the right we do. And Compton and coherent both result in scatter. Compton is actually responsible for 99% of the scatter on our images. And so it's going to be very gray. And that's just the result on the right-hand side where we didn't use a grid for this particular phantom image. In the photoelectric interaction, we're going to interact with an inner shell electron. In this case, the photon is totally absorbed, so it's completely gone. The electron is removed, which is ionization, and that electron is called a photoelectron. So photoelectric, photoelectron. It creates a vacancy, and so we do have a vacancy there. So an outer shell will fill an inner shell electron in, and we get characteristic or secondary radiation that's emitted. But the thing is that that secondary characteristic radiation only travels a few micrometers, which is 1,000 times smaller than the thickness of a dime. So it doesn't contribute to the image at all. So no radiation reaches the image receptor, and we get our white areas on the radiograph. So I went ahead and drew this ahead of time, that if we have 9 photons that are going to be totally absorbed, which are in red or pink or red, or photoelectric, and then we have that at low kVp, compare that at high kVp with only having 3, because photoelectric interactions decrease by a cubed effect. Then if we go from 8 Compton interactions, which I'm showing in blue, they're going to decrease those number of interactions to 4 because they just decrease. At higher kVp, we're going to have more Compton than photoelectric interactions. Even though we have less interactions overall, we only have a total of 7 interactions at higher kVp. The remainder would be non-interacting. At lower kVp, we would have 17 in comparison. But we would have less interactions with matter at higher kVp, but we do have more Compton than photoelectric interactions. Just like at lower kVp, you have more photoelectric than Compton. So at higher kVp, there are more Compton than photoelectric interactions, and we can see the gray on the image on the right-hand side where we use the 100 kVp on this phantom image. An increase in Z number increases photoelectric interactions by a cubed effect. So taking a look at our image, we can see that we have an image on the left-hand side with no extra contrast media, but on the right-hand side, we do. We've added iodine specifically for an IVU, and the iodine has a higher atomic number and therefore has increased our photoelectric interactions by a cubed effect. An increase in tissue density will increase photoelectric and increase Compton interactions as well. So if you look at the drawing here, we can see that as we go from low tissue density, such as air, that the likelihood of hitting a atom or molecule inside the patient is going to be less than if you have higher tissue density. So higher tissue density results in possibility of more interactions with matter. So it'll increase both Compton and photoelectric interactions. Here are some questions regarding interactions, specifically interactions with matter. But which interactions with matter are particularly important to diagnostic radiology? That would be photoelectric and Compton. Which interaction with matter is the source of most occupational radiation exposure? That would be Compton, because we're going to be struck by the radiation coming from the patient. Which interaction results in more patient dose? That would be photoelectric, since there's total absorption. And then finally, does atomic number have an impact on the Compton interaction? And the answer is no. Just photoelectric does. This concludes our video on interactions. Hope you have a great day.